Hello and welcome to Empowered Learning. This particular video will talk about exact cost and how marginal cost is related to exact cost. So what I have behind me is the definition of what exact cost is, sort of derive it and put it together, and then from that we can see how the marginal cost will be related to it. So let's go ahead and get started here. So if we define our cost function being the cost of producing X number of items, and what we mean by that is producing up to X number of items, then we could say that C of X plus 1 is the cost of producing up to X plus 1 items. And so to be very clear on what I mean by that, let's come over here. So let's say I have some cost function C of X. If I say C of 2, then this is the cost of producing exactly 2 items, okay? If I say C of 10, then that is the cost of producing exactly 10 items. And so when we produce these 10 items, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we're taking the total cost of all that together. And of course, with C of 2, that is the cost of producing 1, 2 items together, okay? What this does not mean is, in the case of C of 2, what I'm not saying is that this is the cost of producing just the second item, okay? So we're not defining this particular cost function that way. So here, if we had C of 1, that would be the cost of producing just the first item. C of 2 would be producing the first and the second item. C of 10 would be the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th item all together as a cumulative cost. Okay, so taking this assumption into account, then of course here, if my, let's say X was 10 here, then C of 11 would be the X plus 1 cost of producing the X plus 1 number of items. So that's what I mean by that. So if we take these two things into account, then what we can do to find the exact cost of just the X plus 1 item, or in this case here, the cost of just the 11th item by itself, what we would have to do is take the cumulative cost of all 11 items and then subtract away the other 10, the 10 that came before it. And all we're left with is the cost of that last item. So looking at that in a more general sense, we say the exact cost of the X plus 1 item is just C of X plus 1 minus C of X, where in this concrete example, the X is 10 and the X plus 1 is 11, okay? And so this is how we can find out the exact cost of a particular item if the way that the cost function is defined is that cost is cumulative, okay? So the relationship in between marginal cost and exact cost is that we know that if we take the derivative of cost, that would be what marginal cost is. And we know that a good approximation for the marginal cost would be the difference quotient. And here the difference quotient is written in incrementals here. So the change in cost over the change in the number of units. And so if we write that out here, we have C of X plus 1 minus C of X. That could be a situation where if we had a cost function that looks something like this, then we want to know the rate of change of this point here, which is so many items, there is a cost. And then if we go up here, we add one more item to that, hence the X plus 1, and there is an associated cost with that. So the change in cost, or Y2 minus Y1, over the change in the number of items, X2 minus X1. And so that gives us this difference quotient here. And of course, if our difference in between here and here is relatively small, then this is a good approximation for the derivative. Okay, so taking that and assuming that this delta X here will be fairly small to make it a good approximation of the derivative, we can write it out this way. And of course, if we remove these parentheses here, we see that x minus x would just cancel to 0. And then we have c of x plus 1 minus c of x over 1. And of course, here we know that anything divided by 1 is just itself. So we ended up having exact cost there. So we see that our marginal cost can approximate our exact cost. So give us a nice, what I like to call wet thumb in the wind estimate of that, okay? And so hence that's what we're trying to say here. So now what we're going to do is do an example where we are going to use revenue, cost, profit, and build it from the ground up using price demand functions, and see how once we figure out what the profit of a particular item is at a certain number of quantity of units, we're going to see how the exact cost could also be approximated by taking the derivative of that particular profit, okay, and evaluating it at a certain x value. And so that's what we're going to do next. All right, so now we're at the point where we're going to do an application example. So we'll see how the marginal analysis of revenue, cost, and profit sort of relate to this whole thing of exact cost. In this particular example, we'll actually look at exact profit versus exact cost, but the same concept is there. So let's go ahead and read the problem and see what we need to do. So we have hot dogs will only be sold at a certain arena for $2.50 each. And so all the concession stands together sell an average of about 1,250 of them, okay, at that particular price. Now, of course, the sports arena or whatever it is trying to make more revenue. So of course, they're going to naturally increase the price. So as you know, whenever you increase the price, then the demand for that is going to, whatever it is that you raise the price on, is going to decline. And so we see here that when the price was raised to 320, the hot dog sales declined to 900. Okay. And so at the large events, another thing that we have to take into account is how much is actually costing the food concessionaires. So the fixed cost averages out to be about $910.80. And the variable cost per hot dog is $1.58, okay? And so having all that information, we want to do the following here. So we want to write the price and demand, if it has a linear relationship, write that as a function of x, okay? Next thing we want to do is find the revenue, cost, and profit functions in terms of x and find the domain of those. Afterwards, we want to sketch a graph of revenue and cost to see how that looks. And then lastly, we want to find the marginal profit when the quantity of hot dogs being demanded is 380. And then we want to find out what the exact profit is in selling the 381st hot dog, okay, and see how all that relates. All right, so let's work on this first one here. So we know that since our price and our demand, or P and X, are going to have a linear relationship, we need to find some information that will allow us to either have 2 points or to find the slope in 1 point, okay? So if we read back through our problem here, we see that we know that we're selling at a price of $2.50, and they sold on average about 1,250 of them at that price, okay? So since we know that price and demand are going to be related to one another linearly, we know that our demand is going to be our independent variable and our price is going to be our dependent variable. So when we make our points, we need to make them look like this. So that means here at demand of 1,250, price is $2.50, okay? So next, we see that when they raised the price to $3.20, that it went down from having 1,250 hot dogs to 900. So have 900 here, $3.20. So we have our 2 points, and so from that we can find the equation of a line. So We know that the slope of a line is just y2 minus y1 divided by x2 minus x1. And so we'll just label these. x1, y1, x2, y2. And so we'll just go ahead and plug in. So we have y2 minus y1 and all that over x2 minus x1. Okay. So in the denominator, we have a negative 350. In the numerator, we have a positive 70 cents. Okay. And so from that, keep going. If I multiply the numerator and denominator by 100, I'll end up having this, which means I can simplify to here. And of course, this is the same as saying a negative 7 over 35 times 100. And so negative 7 over 35 is the same as a negative 1/5. That's what that reduces to. And 1 divided by 5 will be 0.2. So if we take negative 0.2 divided by 100, that's like taking the decimal and moving it back 2 spaces to the left. So 1, 2. So we end up with negative 0.002. So that's what our slope would be. Okay. So now that we have that, we can use this along with one of these points in order to find the equation of a line. And so what I'm going to do is use the point slope formula to do it. And I'm going to choose to use this point here, since it has smaller number here. So my y1, in this case, I'll relabel this now. So I'll label this my x2, y2, x1, y1, so that I can use it here. And so my y1 is $3.20. My slope is negative 0.002. And my x1 is 900. Okay. So here I'll just go ahead and distribute. And so to figure this out, if we had 2% of 900, that would be, well, 1% would just be 9, so 2% would be 18. But since we have one more decimal place, we should move back one more, so that should just be positive 1.8. And then from here, we'll add $3.20 to both sides. And if we add all that up, that should give us $5. And so this would be our equation here. And I know I did this in terms of y and x. I'm going to go ahead and change the y to p now, since we're actually talking about price versus demand. So here, this would be a P, this would be a P, 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 and P. And so we have P of X is minus 0.002 X plus 0.5. So this is what our price function would be in terms of demand. Okay. So now we'll go ahead and move on to part B. So part B says we need to find the revenue, cost, and profit functions for this. Okay. So I'm going to go ahead and erase this. So what I'm going to do is focus on the cost function first, because that's the one where we have to, again, piece together some information here. And then I'll do the revenue one second and then the profit third. So for our cost function, C of X, we noticed that in the last sentence, they said that at large events, the fixed cost is going to be this amount and the variable cost is going to be that. Well, we know cost is fixed cost plus variable cost. And so if we put that together here, our fixed cost is just $910.80 plus our variable cost is $1.58, but that's times the number of hot dogs we sell. So this will end up being our cost function, okay? For our revenue function, we've learned that revenue is going to be the same as quantity sold times the price, okay? And so in this case, this will be quantity sold times the function P of X, which means we just take X and multiply that times this function here. And so if we do that, we get this quadratic function. So our revenue function will be just negative 0.002x squared plus 5x, okay? So now that we have this, we know that profit is just the difference in between revenue and cost. So we'll say revenue minus cost. And so here we know our revenue is what this is. And our cost is going to be all this. And we need to make sure that we actually go in and put it all in parentheses here. Okay, so now we just distribute negative and then combine like terms, okay? So we have, oh, I'm losing the 0 there. And so we have 5x minus $1.58. So that should end up giving us $3.42 or $3.42x minus 910.8. And so this would be our profit function. All right. So now what we want to do is, now that we have these particular functions, look at what the domain of each of them would be, okay? And so this is important because, of course, if we looked at this as just a regular math function, of course, the domain for each and every one of these would be all real numbers. But of course, for our situation, that wouldn't make sense because we're not going to order an infinite amount of hot dogs, okay? And we're not going to order a negative amount of hot dogs either. So because of that, what we need to do here is sort of realistically figure out what our domain would be. And so what we'll do is stick to the revenue here, because the domain of the revenue will pretty much control everything else that's going on here. Of course, the cost, we know that as long as we use values for X that are, 0 or higher, that would actually make sense. Although we really wouldn't want to have a demand beyond a certain point, and our revenue is going to control that. So here we're just going to say for right now that X can be greater than or equal to 0, and that makes sense for that problem. All right, so for our revenue function, we notice here that in factor form, it looks like this, and we can actually draw what this is going to be and find out the places where we have x-intercepts. The places where we have x-intercepts would be the place where, of course, if we were drawing a graph of it, it would look something like this. And of course, if this is revenue, then anything below, as it keeps on going down, there's going to be negative revenue, which means you're basically giving product away, which doesn't make any sense. So you wouldn't want to go on the negative side, of course. And same thing here. If you're doing that, you're basically giving product away, and it doesn't make sense. So we want to find out what these 2 points are. Well, to do that, what we need to do is set whatever the revenue equation is equal to 0. So if we do that, we see here that this means that x is equal to 0, or we have negative 0.002x plus 5 is equal to 0. So now, of course, if we sell no hot dogs, we make no money. So that actually makes sense. But on this end, what we need to do is solve for x. So if we subtract both sides by 5 and then divide by 0.002, negative 0.002 rather, then here that reduces to 1, and we could rewrite this as a positive, because negative divided by negative is a positive. Move the decimal place over 3, so we'll do the same thing here. So that would be 5,000 divided by 2, which is 2,500. Okay, so here quantity would be 0 there, and at our next intercept, that quantity would be 2,500. So our domain for our revenue would be x values that are in between 0 and 2,500. Okay, and of course for the profit, that would pretty much be the same thing. Okay, because of course we know that beyond x equals 0 to the left and beyond x equals 2,500 to the right, you definitely wouldn't be making any product if you gave money away. Okay. All right. So here we will say that for the profit equation, the particular domain for this should be the same as the revenue. Although if we went in and actually found out the x coordinates and all that stuff for where we have x-intercepts, that it would be different. But again, we want to make sure that it follows the same thing as the revenue. Okay. So now we've done part B here. So let's do part C. So I'm going to make some room here. And I'm actually going to erase this part so that we can have some room. So our price function here was this. Our cost function is this. Revenue function and then our profit function. So that's a little p, this is a big P. And I'll put the line through it. Okay. All right. So we have that. So now we can get rid of this. And we can work on part C now, which is sketching a graph. So I'm not going to get too particular on this, just going to give you a general idea of what it looks like. So we know our domain is going from when x is 0 to x is 2,500. And so if we look at our revenue and cost, we know that our revenue function looks like a quadratic. And we sort of got the profile from the last graph that it's going to take a shape like this. And so I'll go ahead and write revenue will be something to this effect. Of course, halfway in between here would actually be the 12 or 1,250 we have there. And for our cost function, so we'll say revenue. And so for our cost function, we see that our cost function is linear, starts at a y-intercept. I'll go ahead and put this 910, move this down, 910.8. And then from there, of course, it's shooting up at a slope of 1.58. So that would look something like this. Okay. So that's how those would look. Where, of course, here and here would be our break-even points. And of course, here's where revenue equals cost. And here again, revenue is equaling cost. Okay? So we've taken care of part C. So now what we want to do is do part D here, which is we want to find marginal profit when X is 380, and then find the exact profit of selling a 381st hot dog. Okay? So lastly, if we find a marginal profit, we know that our profit equation is just this. And so our marginal profit would end up being just what the derivative of this is. Okay? So if we do that, we would say 2 times, well, let's say negative 0.002 times 2x for the first one, and then plus 3.42 for the second one, minus 0. We take the derivatives of those. And so this is what our profit equation would be, or marginal profit equation rather. And we want to figure out what is going to be that marginal profit when X is 380. So here, marginal profit is, we just plug it in. Plus 3.42. And so this would be, I'm not going to waste a whole lot of time trying to do that. I'll just do it on my calculator here. So this ends up being 1.9 or $1.90. So, and this will be $1.90 per hot dog. So marginal profit at 380 hot dogs sold will be $1.90. And so another way to interpret that is when the quantity of hot dogs being sold is 380, then we see that the profit of selling the next hot dog would increase by $1.90 per hot dog. Okay. So the last thing that we want to do is find the exact profit of selling the 381st hot dog. So from what we remember earlier, we know that one of the ways that we can find the exact profit here is we would say profit of the X plus first one minus profit of the X one. Okay. And so here, if we let X be 380, then we just need to find the profit of 381 minus the profit of 380. And this would be the exact profit. And so, of course, to do that, we would need to use this particular function here and plug it all in. And I'm just going to make life simple for myself by using my calculator to do that, give those values for me here. So I'm going to go ahead and plug in this function, and I'll get us our answer here. So we have a negative 0.002 x squared plus 3.42 x minus 910.8. And what I'm doing is I'm putting this in the graphing part, and I'm going to do, the second calculate to get it to evaluate a value. So for those of you that are wondering how I'm going to do this, that's how I'm doing it. So after I'm done with this, I'll set my window and make sure that my window can handle these type values. So I'll set my x min to 0 and my x max to 2500. And then from there, I'll hit second, calculate, and then select number 1, meaning value. And of course, it'll do some graphing or whatnot, but I'm just waiting for the x equals. And then I plug in 381, and that gives me 101.898. And then I'm going to do the same thing for x equaling 380. So I'm just going to type in 380, plug that in, and I get exactly 100. So we take the difference of that, that would be 1.898. And that would be in dollars here. Now, the thing that I want you to notice is that when we did this, the exact profit was almost $1.90, whereas the marginal profit when x is 380 was $1.90. Okay, so you see how the marginal profit of taking x quantity, the quantity of x, is approximating what the exact profit is on the x plus 1 item. Okay, so you see how close these two are together here. And so again, that's why we were saying that in terms of just a general function, the derivative of the function would be a good approximation of this. And of course, in terms of cost, we were saying that marginal cost would be a good approximation of exact cost.